So I didn't want to write this again, but you may recall 2 weeks ago we started momentum. And we spent 2 weeks on momentum, and I said momentum is a different way to do physics. It's a different way to do motion problems. Rather than forces and detail kinematics, we have collisions and interactions. They're easier solved with momentum. And I told you there's a third one coming, and it starts today, and it's energy. And these are good for sort of initial, final problems, as you'll see. So we're about to spend 2 weeks on energy. That's the plan. That's what we're doing. All right. Now that can go away. Okay. 2 weeks on energy. If you read any introductory physics book about energy, they all will say energy is hard to define. Right? That's always how the chapter starts. It's really, we can't really define it in any good way, which is sort of ridiculous. There's a technical definition of energy, but when you're teaching intro physics and just learning it for the first time, it is a little bit hard to define. Okay? So everybody who's ever taught intro physics, I don't like to generalize too much. Everybody who's ever taught intro physics has struggled with how to define energy. And everybody goes, wait, I have the ultimate analogy. I have it. Energy is the currency of physics. Oh, and you think I'm going to be famous for this analogy. Currency meaning money. Okay? You all know what money, Venmo. Energy is the Venmo of physics. Okay? And the analogy is if you have a lot of Venmo, you can do a lot of stuff. You can make things happen in the world. And if you don't have much Venmo, you can't do anything. That's the idea. If the system has a lot of energy, it can make a lot of things happen. It can make a lot of changes. And if it doesn't have any energy, it can't really do much. Okay? I'm going to be famous for this analogy that I finally thought of. And then you keep reading the book, and everybody thinks of this analogy. Right? This is the analogy used for energy. Some books, I have one book that I swear to God goes on for like 3 pages of this analogy. It's like there's like a central bank and a Fed, and there's like all of its currency manipulation. It just goes on and on. It takes it way too far. It's not worth going that far. But it is the idea. That's the only simple definition we have. So what we do then is we go straight to the first kind of energy. We don't get all high-minded about it. We just go straight to kinetic energy. And this is like one of Newton's laws. If you've taken any physics, and if you haven't, that's okay. But if you have, you know the definition of this. It's the energy, the second word is a word that I can't define, of motion. When something is moving, it has kinetic energy. That's the idea. It's in a new unit. It's in kilogram, meters squared, per second squared, or joules. That's O-U-L-E-S, which is J. Joules. Named after Mr. Joule. So the idea is it's the energy of motion. The more motion you have, the more energy you have. So first let's get that sort of in our head. So this is a system I want to interact with, and I want to make a big change on this system. And I'm this system with my cart. So if I don't have a lot of motion, I have a low amount of motion up like this. I'm not going to have much of an effect on this thing. Nothing. Very low energy. We want to do it with high energy. Does anybody want to join me on the cart and do it with high energy? That will lead to bad things. Okay, here we go. This is high energy. High energy. I made a big change on the system because I was moving fast because I had a lot of kinetic energy. So let's look at the formulas for energy. Okay, there's translational kinetic energy, which you just witnessed. My leg got caught in a little angle and I nearly broke my femur, which has never happened before. K equals 1/2 mv squared. So not only does it depend on motion and moving fast, it goes as v squared. So as I really start moving, my kinetic energy goes way up. This is the one that you learn about all the time. And this is for translational, something with mass m and velocity v. Okay, but here we've already done rotational motion. So we can go ahead and write down the rotational formula. There is also rotational kinetic energy. And that is K equals, and remember all the rotational formulas are just like the translational formulas. You just substitute the rotational values. 1/2 is the same. The rotational mass is the moment of inertia. The rotational velocity is the angular velocity. So it comes out the same. So say you have a disk, mass m going around at omega, 1/2 I omega squared. And I want to be clear, translational and rotational kinetic energy are the same thing. They're just energy, they're all in joules. We could go through this unit and say, what is the unit of I, the moment of inertia, kilogram, meter squared? What is the unit of omega? Radians per second, radians squared per second squared, right? And you say, oh, but radians aren't real. So kilogram meter squared per second squared. Same unit. Okay. And then if you broke this down into individual little points, it's really just little masses moving in V. And if you added up the 1/2 mv squared of every little atom in this disk, you'd get the same thing, 1/2 I omega squared. You can derive what I is this way. We just didn't do it that way. Okay? Okay. Let's do a few bullets on this one about energy. Okay, here's some bullets. I've decided to make my bullets actual bullets like that. One, here's the good news. It's a scalar quantity. So this one is easier than momentum. Momentum was a vector. Never sneak up on it from behind one lecture. Momentum was a vector that made it more difficult to deal with, vector quantity. This is just a scalar, so that's good. Another thing about kinetic energy is it's always positive. These are both about kinetic energy, not necessarily just energy. Okay? So this is kinetic. This is actually both. Energy is always a scalar. Here I'm just talking about kinetic energy. Always positive because the v is squared. So even if you have your velocity backwards, if v is negative, you're going to square it. You can't possibly have a negative kinetic energy. This is related. V and omega are essentially just magnitudes. And the direction is irrelevant. So here is something, a mistake. Let me get a look at you guys. A mistake 27% of you are going to make on the exam. Ready? Based on just your general look, I'm going with 27%. Is you're going to do a problem, and you're going to say, okay, a mass takes off at V naught. I want to do this with energy. The first thing I'm going to do is calculate energy in the x and energy in the y. 1/2 mvx squared and 1/2 mvy squared. No, don't do this. Okay. Energy does not have directional components. It is a scalar. The only way to start this problem with energy is to say that the energy has nothing to do with direction. 1/2 v mv naught squared. Do not do this. People will still do this. People that don't come to lecture. You do not break it into components. You just stick the magnitude in this formula. It's because it's squared. We can't break it into components that add together because it's squared. It's not proportional to v. It's proportional to v squared. Okay. And then there's this idea that energy is constant. It can't be created or destroyed. And that is true, except for one thing. Is K, kinetic energy, depends on your reference frame. So if I see something moving by me, I say it has kinetic energy. If I start moving with it, I say it doesn't. So when you say energy can't be created or destroyed, BS. I can destroy energy. I can just move with the object. There, its energy's gone. Okay? So energy can't be created or destroyed within a frame of reference. It has to remain constant within one thing's frame of reference moving. Technically, it does. Sometimes people just wonder, wait a minute, if I'm moving with the object, doesn't K can't be suddenly zero? The answer is yes. The whole thing we'll talk about later about conservation of energy That's from a specific reference frame. Okay, that's big picture on kinetic energy. Now, we're going to calculate a couple. It's a pretty straightforward formula, but just for fun, we're going to calculate it. And I need somebody to be the timer. Who here is into steam pump and wants to admit it? No. Is anyone into steam pump? No steampunk doctors here? Okay, who wants to use this timer that looks kind of steampunky? Look at this. 1912. It still works. Look at that. There you go. Come time. And okay, we're going to calculate my kinetic energy. Just time me from here to here, which is 3 meters.
Wait, hold on.
Oh yeah, you hit it once to go, and then you just read it. I don't know how to read it. It's in like old-timey English. Can you read it? Okay, good. Here we go. I'm going to start on the carpet and start here, and the other end of the bench go over there. You ready?
And here?
Just from this end to that end. You ready? Go! Stop.
Okay.
What'd you get? I can't read it. 1.81. Now wait there, we're going to do another one. Okay, what's my kinetic energy then? 1/2 mv squared. So if this were a problem, you'd have to estimate my mass. The car is heavy, 80 kilograms. But now V, I went 3 meters in what? 1.81 seconds. So it's just the normal V you're used to dealing with squared. I didn't work this out ahead of time because I didn't know what would happen. Okay, so I don't know. Like a little less than 2 squared, 3 over 2, 240, about 120 watts, 120 joules. I get 120 joules, but I did it in 121. Okay, so we just did that. Well, that was fun, right? Let's do rotational. Wait, hold on. We're going to do rotational now. Let's do rotational. So this is like a rotational thing, and I'm going to do the skater trick to get my speed really high. Okay? And once my speed is high, calculate or measure 2 laps around. Okay, I'll see you and then start and then 2 around. So first let's just get a little speed going here. So the reason I can do this is angular momentum, which we didn't cover, but that's okay. Okay, go ahead and do 2 laps around. Let me know when you're done before I vomit.
I'm done.
Are you done?
Yeah. I don't know if this was 2 or 3. I think it was 2. It's 2.11.
2.11 seconds.
2.1.
Okay, so we're going to do K equals 1/2 I omega squared. So this is just a little bit of practice. Okay? 1/2 is 1/2. What is my moment, though? Now, we don't want to make you do approximations. That didn't go well on the first exam, right? But by approximation, I would say, is my moment, if I'm roughly a disk like this, is, what was the disk? 1/2 mr squared. Wait, no, we're done. That's the last one. 1/2 mr squared, right? So there's a half due to the energy formula. There's a half due to 1/2 mr squared. My mass, oh, I don't have the part. Oh, but the chair's heavy. 80 kilograms. And then the radius, if you approximated me as a disk, I don't know why I keep doing this, but like would be like this far. What is that? 20 centimeters, 0.2 meters. Mr squared. Right? So there's I. We just calculated I. And then omega. See, I went around twice in 2.1 seconds, or well, let's say 3 times. 3 rotations in 2.1 seconds. Okay? So 3 rotations, you'd replace that with how many radians? Radians per second. 6 pi radians per second. Each rotation is 2 pi, so 6 pi radians. So you do all that, and you get a number. And I didn't even estimate it. It'll be less. Well, I don't know. I don't know what it'll be. So I'm just going to go on, and if somebody has the number, shout it out. Shout it out. I didn't throw it this year.